Welcome back! Now that we've analyzed rational functions algebraically, we'll use what you learned in the last lesson and make the leap from sketching asymptotes to actually graphing rational functions. This is your last lesson with new material in Unit 2, so be sure you have your guided notes ready and let's go! In the last lesson, you learned some important tools that will help you graph rational functions. You learned how to find domain restrictions and determine whether the function will have vertical asymptotes or holes. You also learned how to find any non-vertical asymptotes by analyzing the function and comparing the degree in the numerator to the degree in the denominator. Now you can use what you learned in the previous lesson to analyze the function 1 over x and record everything you know about it in your guided notes. What do we know about this function? Its domain is all real numbers except for x equals 0, where it's undefined. And because there are no factors to cancel out, it doesn't have any holes, and the line x equals 0 defines a vertical asymptote. Because the degree in the denominator is larger than the degree in the numerator, the function has a horizontal asymptote at y equals 0 and no oblique asymptotes. Let's sketch in those asymptotes. If you know what this function looks like, you can graph it from here. If you aren't quite sure, you can use the same technique we'll use throughout this lesson. Plot a handful of points until you get an idea of what it looks like. Go ahead and do that now. In your guided notes, fill in the x-y table for y equals 1 over x and plot the points on the graph provided. Great! You should have gotten these points in your table. And plotting them on the coordinate plane looks like this. Following the asymptotes we already found, we have two pieces of the function, one in the first quadrant and one in the third quadrant. Now that we've graphed 1 over x, take a moment to compare it to 1 over x squared, which we graphed in the last lesson. How are these functions similar and different? Why do they each take these shapes? Record your observations and conjectures in your guided notes. I noticed that the piece of each graph that's in the first quadrant is very similar. They have the same asymptotes and the same basic shape, but the other piece for each function is different. 1 over x has a piece in the third quadrant, but 1 over x squared has a piece in the second quadrant. Why did that happen? Did you notice that by squaring the denominator of 1 over x squared, the function will always be positive? That gives us function values that are always greater than 0. But 1 over x has both positive and negative values. Functions of this form are a subset of the rational functions, and they are called reciprocal functions because they are the reciprocals of the parent polynomial functions. For example, 1 over x is the reciprocal of the parent linear function x. And 1 over x squared is the reciprocal of the parent quadratic function x squared. Once you know how the reciprocal functions behave, you can start to apply transformations of the type you've seen before. For example, now that you know what the graph of 1 over x looks like, how would you graph f of x equals 1 over x minus 5 plus 4? Use your guided notes to use what you know about the parent function, 1 over x, and transformations of functions, and try graphing this transformed reciprocal function. Welcome back! I started with the parent function, which we know has asymptotes at x equals 0 and y equals 0. Then I thought about the denominator, where we are subtracting 5 from x. What transformation does that produce? Subtracting 5 from x means that the function will shift to the right 5 units. We also know, by looking at the denominator, that the transformed function will be undefined when x equals 5, confirming what we can now see on the graph. The vertical asymptote at x equals 0 on the parent function also shifts to the right 5 units, and will now be at x equals 5. Next, what happens to the function when we add 4 to it? Adding 4 to a function shifts the function up 4 units. That means that the horizontal asymptote will also shift up to y equals 4. There are no other transformations here like scaling or reflections, so the basic shape of the parent function does not change. We've now graphed our function f of x using what we know about the parent reciprocal function and our previous knowledge about transformations of functions. And in the future, if you need to graph a basic reciprocal function with transformations you're familiar with, go ahead and try using the method you've just seen here. But now take a look at this new function. Could you apply transformations of a reciprocal function to graph this one? Well, this isn't a reciprocal function, is it? What type of function is it? Yes, it's a rational function like the ones you analyzed in your most recent lesson. Use your guided notes to factor this function as much as you can, and then record everything you know about it. Try graphing as much of it on your own as you can, and then we'll go over it together. Here's the factored form of the function. And what do we know about it? The factor x plus 2 cancels out, so it has a hole at x equals negative 2 and vertical asymptotes at positive 1 and positive 3. That means that the domain contains all real numbers except negative 2, 1, and 3. The degree in the numerator is the same as the denominator, and 1x cubed over 1x cubed is 1, so it has a horizontal asymptote at y equals 1 and no other asymptotes. If you didn't do it already, now is a good time to sketch in all 3 asymptotes. What can we do next? We know that this function has a hole, but we don't know its precise location. How could we find the location of the hole if we don't have a function yet to examine? Here's a useful tool you can use to figure that out. Temporarily ignore the common factors that we canceled out and focus on just x squared minus 3 over x minus 1 times x minus 3. Using this modified version of our function will tell us what y would have been if the function was defined at x equals negative 2. Substituting negative 2 for x gives us y equals 1/15. That means that the hole is at negative 2, 1/15. Sketch that in also using an open circle. What can we do next? We need to know what the function is doing in these various sections, don't we? It could look like this, or like this, or like none of these. How can we narrow it down if we want to really understand this function and graph it without using technology? We'll need to plot enough points to get a good visual representation of what the whole graph looks like. But we don't want to just choose random points. We should be intentional and choose a few x values near each asymptote along with 1 or 2 values a little farther out. To illustrate that, let's take a look at the x values I'm going to use. I'm going to use negative 4 and 0 for the area to the left of the vertical asymptote at x equals 1. 1.5, 2, and 2.5 for the area between the 2 asymptotes, and 4 and 5 for the area to the right of x equals 3. These points should give me an accurate picture of what this function looks like. Evaluate the factored form of this function, ignoring the 2 factors that canceled out, at the x values shown in the table, and plot the resulting points on the coordinate plane in your lesson notes. Feel free to use a calculator and round decimals to the nearest tenth if necessary. How did you do? Here are the values I got in my table. Do you think using the factored form was the most efficient way to find all of these values? I think it's actually easier to find the y-intercept by looking at the unfactored form of the function. When x is 0, each x term drops out, leaving us with only the constant terms, which in this case are -6 over +6, which reduces to -1. When plotting points to graph a rational function, it's always a good idea to use this technique and the unfactored form of the function to identify the y-intercept, provided that the function is defined at x equals 0. Here are the points I found plotted on the coordinate plane. Now we have enough information to graph this function, using the asymptotes and plotted points as guidelines to help us draw smooth curves. Remember to skip over the hole. Before we move on, there's one more thing you can do with the factored form of the function. Examining the factored form of the numerator will show you the function's x-intercepts. Using the factor that didn't cancel out, x squared minus 3, and setting it equal to 0 tells us that the x-intercepts are plus or minus the square root of 3, which is about 1.7. We can see both of those values here on the graph. One more confirmation that we have correctly graphed this function. Next, we'll take a look at a chart, which has also been provided in your PDF guided notes that will guide you through the whole process of sketching rational functions without using graphing technology. Then you'll try one on your own. Let's walk through the steps in this chart together. First, to find any discontinuities, use the denominator in its factored form to find any vertical asymptotes or holes. If there are any holes, you can find their y-coordinate by evaluating the simplified function after canceling any common factors. Next, we can find any non-vertical asymptotes by analyzing the degree of the numerator and comparing it to the degree of the denominator, as you learned in the previous lesson about analyzing rational functions. Once you've found any asymptotes or holes, you may find the next steps easier if you sketch them on your coordinate plane at this point before moving on. Find any x and y intercepts by using the techniques you saw in the last example. And finally, find any additional points as needed, making sure to include at least a few points from each section of the graph. Now it's your turn! Use the table in your PDF guided notes and everything you've learned to sketch a rational function on your own. Use the space in your guided notes to graph g of x without using any graphing software. Okay, here's the factored form of this function. The function has a vertical asymptote at x equals -1 and a hole at 1.25. The degree in the numerator is exactly 1 greater than the degree in the denominator, so we know it will have an oblique asymptote. We can use long division to find the quotient, which gives us the oblique asymptote at y equals 1/2 x minus 1. After plotting some points on either side of the vertical asymptote, you should have a function that looks like this. Now that we've gone over all of the steps to graph rational functions without using graphing software, be sure to finish your guided notes and complete the activities and practice in your PDF. Your next lesson will summarize and wrap up everything you've learned about rational functions. Thanks for watching! Hey, hey.